Hi, in this video, we want to take a look at spatial temporal data. All right, so what we've got going on is that we're interested in some data that is connected to locations, like coordinates, latitude, longitude, but it's also connected to time. So normally, if I was doing time series, I could just do time series analysis. Or if I was doing spatial statistics by itself, I would do spatial analysis. Here, we've got both of them going on. All right, so how we typically approach this when I have spatial temporal data is that round one, I look at the data without considering spatial coordinates at all, and I don't consider time. So I look at the data, don't consider coordinates, don't consider time. Now, round two, I pick whichever one is really, I feel is more important, more interesting, more comfortable for my skill level that I'm interested in. So I'll go through, I'll do the time series analysis without considering spatial, or I'll do spatial analysis without considering time series. All right. And then I go the other way around, and that's round three is where I'm doing the other one. Round four of our analysis, typically for spatial temporal data, is I'll try to analyze spatial and time at the same time. Now, that can get very complicated. That can get very messy. A lot of things can be going on. So what we typically do, we start taking like coarser components. So with regard to like time series, maybe instead of doing things by day, I do them by month or quarter. And for spatial, instead of doing things maybe by county, I'll do them by state. Or if I have things over a grid, I'll take a coarser grid just so that I'm reducing it down to something easier for a human being to understand. All right, so the example that we're going to work through is from Applied Spatial Data Analysis with R. Here's the website, asdar-book.org. And you can download this for free from the University of Central Florida's library if you're a student. All right, I've modified the code quite a bit. And so that's just to make it more consistent with how I feel like code is easier to read when you're teaching. All right, so the introduction. So we've got four phases when I analyze spatial temporal data. First one is I don't consider time or location. I just analyze like my data frame. I don't worry about where it is. I don't care about when it is. Next, I'll do one of these two, whichever one either is more interesting to me, more important for the project, or whichever one I'm better at with my skill set. And then after that, I'll switch it. I'll go the other way. So if I did time series analysis first, I'll do spatial data analysis second, or I'll do spatial data analysis first, time series second. And then after that, I'll try to, or I won't try, I will analyze in terms of location and time simultaneously. Now that can get very messy, and so we tend to take things over coarser measurements. Like instead of doing things by month, I might do them by quarter or by year. If I have a grid, I'll take a coarser grid, aggregating values over the grid to make it easier for me to understand what's happening. All right, so something that we need to talk about next is the regularity of our data. All right, so regular time series has consistent intervals of time between observations. So think of like the stock market. Stock market, it's day, 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 day. It's very consistent, or time, whatever level you're measuring. The stock market has a very regular aspect to it. Now, irregular would be like we have a minute between observations, then we have 5 minutes, then we have 10 seconds. And so it's not a consistent amount of time between our observations. Spatial data, well, regular for us will refer to our observations being on a grid. And when I say a regular grid, that means that we have constant distance in each direction between our points. Now, regular spatial temporal data will be regular in terms of the time series and the spatial data. So spatial temporal data may be regular in time series and irregular in spatial, or it could be regular in spatial, irregular in time. And we just need to know what we're dealing with as we work with it. Now, if I have sufficient data, something I can do, if I have irregular data, but I have a good amount of it, if I have sufficient amounts over each subinterval, I can go through and I can aggregate to make my data regular using aggregate functions such as max, min, sum, mean, median, stuff like that. All right, so some things we need to think about when we're analyzing spatial temporal data. We need to think about, with respect to time, do I have temporal durations? So am I talking about my measurements are over like the number of collisions at an intersection over a week? Or am I talking about individual events, so instantaneous? So here, there's like, we could have, so if I have a duration, the number of events per like quarter, or it could be an instantaneous event at one particular time or one particular measurement. Now, with respect to location, we can have it stationary or moving. So if we're talking about stationary, maybe that intersection that we were talking about a moment ago, that would be a stationary spatial temporal data. But if I'm interested in, let's say I've got a tracker on an animal, or let's say a dolphin, turtle, something like that, and I'm tracking its movement in the ocean, well, that would be a moving spatial data. All right, we're going to be focused on the space-time package in R. And so this has a pretty good structure for how to approach this type of analysis. What it does, it takes the SP package for the spatial component, and it takes zoo and XTS for the time series component. And so that way it can grab the strengths of both of those. And so, in space-time, time is represented by time intervals or time instances, and it's able to handle either durations or instantaneous measurements without any problems, but it's implicit to this. So you have to actually look to see aspects like end time inside the class to know which one which type you're dealing with. It can handle regular or irregular layouts. It has a pretty good setup for trajectories. And we have data frames attached to, and attributes attached to, time and location. Here is some citation information for the package. All right, so this is copied and pasted from the Journal of Statistical Software. See if I can get this all the way on here. Oh, I need to make it a little bit smaller. There we go. All right, so how this works is that there's a hierarchy of structures. So the lowest is the STT, well, and then STI, STS, STF. Now these do not have data frames in them. So this is the data with respect to space and time is in here. If I have a corresponding data frame connected to the space-time observations, then we put a DF on it, and we notice that there's a data frame. So here, the STT is for trajectories, STI is for irregular, then STS, sparse lattice, and STF is for a full lattice. So here is the space-time geometry aspect, and here is the data frame. All right, so the ST class is an abstract class used for spatial temporal data where there really isn't much constraint on what's going on. The STT is for trajectory. The STI is for unstructured spatial temporal data. And so in spatial locations, in spatial observations. And so there's no grid aspect going on this one. And then the STS is for partial space-time grids, and the STF class is for full space-time grids. And so what these are doing for us is that this is how the space-time package organizes what's going on. So each of these is a class in R for a class of object. And so when I pass these objects to a function in R, R looks at, well, it's this type of class, therefore I handle it this way because I know which features it has. And something that's going on, you'll notice that for all of these, the ST, this is fundamental to all of these. There's a spatial component, which is for the SP package, or it uses SP package classes. For time, it's doing everything in the format of the XTS package. That's a major time series package. Also, zoo is used, by the way, and in-time is for this time format for storage. And that this in-time helps tell R if we're dealing with instantaneous data or duration data. All right, so the more fundamental, more basic arguments are SP, which is an SP objects. So it's spatial, such as spatial points, spatial polygons, something like that. For time, it's going to be usually of an XTS class, or it could just be a time vector. And so here, you'll notice that these are typical of the zoo package. In time, and this specifies the endpoints of our time intervals. So if I see that I have, in my data, I see a time, and then I see that end time is different, then I know that there's a duration. That's how R figures it out. If the data time and the end time are the same, it's instantaneous. And traj is for trajectory, and then the data is my data frame connecting to each space-time observation. All right, so let's look at the construction of ST objects. All right, so the data here is from the North American Breeding Bird Survey for the Eurasian collared dove for 1986 to 2003. And here are the people who published it. So first thing I'm going to do, I'm going to load my coordinates. All right, so here it's stored in a table, and you can get this data from that website. I showed it, the textbook's website I showed at the beginning of the video. It doesn't have a header, so it's false. Now, what I'm going to do, I'm going to take what I just loaded, and I'm going to use that to be my coordinates. I'm going to make that into an SP spatial points object. Need to set up my projection. So go on with WGS84, a good default choice. And here I'm just doing a quick plot just to see what it looks like. All right, so what's going on? This is the United States. We can see that this is Florida. These points are in Florida, and these other points are in other parts of the United States. I can't tell where because I didn't put down a background on it, where the states are. All right, so now that is my spatial aspect. Let's go ahead and take care of the time. And so we know that the years are from 1986 to 2003. So what I'm going to do, I'm going to take the years. I'm going to append New Year's Day onto each of the years as a character string, and then I'm going to convert that to the date. And you'll notice I have it in the year, month, day format, which is the best format you can get. Now I'm going to load the data frame. So previously I got the spatial coordinates, I got the time of the observation. Now I'm getting the data frame on there. And so I'm loading the data frame, which is also on the website. And if you look at the data, you'll notice that there are some negative values. Well, this is a bird survey. Negative values don't really make sense. What they did is they coded missing values as -1s. And so whenever I see a -1, I need to override it with an NA. Now what I'm going to do, I'm actually going to build my space-time object. All right, so this is going to be STF data frame. Here is my spatial points. Here is the time. And now I take my data frame. And so I'm taking what I loaded previously, converting it to a matrix, and then converting it to a vector so it can be counted as a data frame of counts. Probably a more efficient way to go about this, but this is how the author chose to do it, so I'm sticking with their method. And so now we can take a look at what we've got. All right, so we can see that with respect to space, we have 253 locations, we have 18 different times, and we have one variable, which is counts. All right, let's just go ahead and hit summary just to take a look at what's going on. All right, well, we can see 4,554 is the total length. Here is the class, and it is an S4 object. That doesn't really help me too much. So let's go ahead and do a plot. All right, so I'm going to use the Spacetime package, the Spacetime plot function, and I just drop it straight in. And here's the plot I get. And you'll notice that it breaks it up by time by default. And we can see that it's giving the spatial location, and it's using the count to determine the colors. Now, when you check this out, you'll notice that there's just a few colors. So one of the things that's going on is that points are over plotting, which isn't favorable. But could play with that, could make it a little bit smaller, put some transparency if I wanted to. But something that I immediately realized very quickly about this is I see a lot of black and very little of the rainbow colors. Black is here, and then the rainbow colors are here. And the system will only go as far out as its maximum. So I think 131 is probably the max of all the observations. So this is definitely a skew right distribution for the counts. An alternative way to construct the object from data frame tables is by using the spacetime function stconstruct. And this help documentation, the help documentation, talks about in long form. This is with all variables in one long column. So think of that as in like tidy presentation, good for ggplot format. Space wide format, where different columns represent time series for different locations. And then time wide format, different columns represent different moments or periods in time. And so these are standard ways of formatting space-time data sets. And so here, space wide, each column is a time series for a different location. Then time wide, different columns represent different moments or periods of time. All right, so now let's go ahead and construct it. I've got the stconstruct function from the spacetime package. Here, I'm pulling in that data frame. Here, space is my spatial coordinates. Time, I'm pulling in as a list. Time object is there. And if I hit all equal, we'll see that yes, in fact, I have exactly the same object, just built in a different manner. So everything is good either way. And so now if I go through and I plot it, everything's going to be the same as the previous plot, but I built it with a different object. All right, so something that we want to be able to do is do selection, addition, and replacement of attributes. So space, the space item can either be a character vector to select the spatial locations with matching row names. Space could also be instead be a spatial object. So we can either go character vector or spatial object. Time can be a character string. It has to be in standard format. And things work, we can also use the XTS objects where, I feel like that's probably the better way to go for time if you have that available. So let's go ahead and run through an example. This is from the website once again. I'm going to go ahead and pull in the map of Florida. So what we're going to do, we're only going to look at the Florida observations. We saw a good number of them a good number of the observations are in Florida from that plot I did initially. So let's go ahead and get what we're going to do in this game plan. We'll look at just the Florida observations. All right, to start out, I'm going to use the maps package to get the Florida state map. And here is its silhouette. Notice that the keys are missing and Lake Okeechobee is not plotted. All right, so now what I want to do, I want to go ahead and set up the spatial polygon. So I'm going to use map tools, map to spatial polygon. So I'm taking that map, I'm going to convert it to spatial polygon. So I'm just grabbing that map I had previously. Now, after I do that, I haven't set up the projection. I want to make sure everything has the same projection so everything makes sense as I do my analysis. So what I'm going to do, I'm going to grab my space-time object. I'm going to grab its projection string, and then I'm going to assign that to my spatial polygons object. All right, so now let's go ahead and inspect that. We can see that we have 58 for space, 18 for time, and one variable, which was counts. And if I want, and we can go into more specific aspects of the object. So now I just want to look at look at over those different times for each of the years. Space is 253, time is 6, and variables is 1. If I'm interested in the counts aspect, space is 253, time is 18, same number up here, and variable is 1. And if I want to go with Florida, then the years, then the counts, we can see that space is 58, just like it was up here. Time is 6, like it was here, and 1 once again. The more I specify, the more specific we're getting of outputs. All right, so let's go ahead and take a few looks at our space-time object. And so its mode is a list, which makes sense because lists can take any object, any order. They just take whatever you want, put them together in one object. Its length is 1. And if I want to specify things, specify the counts, I can get the number of counts is 4554. Another way to get that, so you'll notice that here I'm using the brackets to extract what I'm interested in. Here I'm using $ notation. I can use either one. In general, $ notation is faster. Now, that data was very, very skewed. That was very clear for that. Now, there might be zeros in there. So skewed data, if all my data is positive, I'm going to probably be using logarithms. If there's zeros in there, log won't work out. So a better choice in that situation is the square root transform. Honestly, any nth root I could use, but to keep things algebraically consistent to what we're familiar with, most of the time we go with either logarithms or square roots. Here we're picking square roots. I use square roots a lot at work, by the way, for my visualizations when I have skewed data, because it accepts those zeros. All right, let's look at overlays and aggregation. Okay, so if we take a look at the STF-DF, so here this is a space-time grid with a corresponding data frame. And so we have n spatial locations, m times, and n times m observations are available. All right, to build this, I specify my SP object, I specify my time. Now, what I'm going to do, so I've taken, so this is my STF for Florida. And now this is not, okay, I should not have a DF here. So this is an STF object, not an STF-DF, because there's no data frame. All right, so what I want to do, I want to take my Florida data, I want to take my Florida polygon, spatial polygons, and I want to make sure that I have spatial polygon for Florida. I want the data observations for Florida also. So what I'm going to do something like a left join. I'm going to use the over function. Now, other packages have over for spatial data. For spatial-temporal, I need the space-time version of over. So what's happening is I'm doing a left join here on this X. Spatially, this is a left join. So what I'm doing, I'm saying this is the area I'm interested in. I'm saying take all of the data from here that is within this range of coordinates. Now, when you need to aggregate, go ahead and add them up. And it's okay to remove missing values. And let's see what happens. All right, and so here are the counts. Here are the square root of the counts. And so now I want to create that STF data frame. So what I'm going to do, I'm going to grab the spatial temporal data. I'm going to tack on the count and square root of counts data, and I'm going to tack it onto there using new. And I'm going to specify that this is the class I want. And so now I've got what I want. So it's only showing the data frame aspect when I hit summary, but there is a connection to location and time now. And so now let's go ahead and start doing some aggregation. What I want to do, I want to add up all of my observations for each date. All right, so I'm going to go through and we use the aggregate function. Here is the object I'm adding up. Here is my by statement. Now, that's very different from typical base R aggregate. The by is a space-time object, sum just like usual, and drop in missing values. And so here we can see the number of counts and square root counts added up by this. And you'll notice that this will be the sum of square roots from the computation. Now I can also do 5-year averages, which is very similar, but this time I just specify 5 years. And it'll do things very nicely for me. And when I do that, here's what I get for my mean when I plot it. You'll notice that here is the 5-year average for each of the locations. And so at each location, it's looking over that window and go through and take averages. Now for visualizations, first one that we can use are the multi-panel plots. And so if I do space-time plot, I just go through and there's a lot of things I can specify. Just like with regular old plot, I've got a lot of tools for specifying what's going on. It can get a little bit complicated. Start with the objects and then start building out the rest if you're interested in going this route. And I can start seeing individual aspects very nicely. And notice that I'm doing this over a mean like this. So the average at each location over the 5 years. And so we can see that towards the end of data collections when we start seeing larger values. We can also do space-time plots. All right, so what this does, this incorporates time series and location. So there's a lot of code here. And you really have to have control over your of how you're putting down your locations. What this code here is doing, that this is setting it up so that I have I have my locations sorted by their count numbers. And when I do this, once again, it's stplots. I put the mode of xt, and see, I can see the location where we have more and less over here. And this gives me an idea year by year of when did we see more, when did we see less. Now we can also do animated plots. Okay, so animated plots don't really work for an R Markdown document, and they don't work for a textbook either. And so this code really is lacking, but the owner owns this, I own this, that it's really not the best presentation of animated plots, but we do have those options. And so if we go through, we can set up using the PLM package to be able to get some animated visualizations going. It takes quite a bit of work to kind of get this the way you want it. Okay, I kind of just want to jump to the punchline. And so what this is supposed to be doing is presenting state by state. So over here is state by state animation of the time series. Here is variable by variable the animation of what's going on. So here, for each state, each variable is plotted and animated. Over here, we go by variable, and within the faucet, we see that each state is plotted and animated nicely. All right, well, that's all I've got for you. Take care and goodbye.